So, absolute values. When taking a look at what an absolute value is, we actually have to understand how it's denoted and what it actually means. So, the way I'll define an absolute value is I'll say that it'll be expressed and denoted by these two lines that will surround a number or expression. So whenever you see these two lines, regardless of it being around a number, or for example, if it were around a quadratic expression like this, you'd be taking the absolute value of it. And the way we actually express how an absolute value actually looks like is we have to, in simple terms, look at the number's distance from 0. So how far it is away from 0, regardless of direction. So despite it being negative or positive, we're taking a look at its distance from 0. So it'll always be a positive number. So in simple terms, it's an absolute value is just turning a negative, or if a number is positive, you're changing it into a positive. So let's say we have the absolute value of 5. So we had a number line here, and we had 0. 5, you'll notice that 5 is going to be 5 spaces away. So when we take the absolute value of 5, our answer is going to be 5. Let's say we took the absolute value of a number like -5. So notice how -5 is still 5 spots and places away from 0. So our answer to the absolute value of 5 is going to, or -5 is going to be 5. So whether the number is positive or negative, its absolute value is always positive or 0. So now moving on to some real applications of this. So we're asked to find the absolute value of 5 times -6 minus 7 times the absolute value of 3 minus 1 cubed. So let's do this. So we have to do whatever's inside of our absolute value sign to begin with. So we have 5 times -6, which is -30, minus 7 being multiplied by the absolute value of 3 minus 1 cubed, which is going to be 2 cubed. Now let's take the absolute value here. So we get 30. The absolute value of -30 is going to be 30. Then we have -7 times 2 cubed, which is 8. So now we can evaluate this. 2 minus, and 30 minus 7 times 8 gives us -26. So our answer here is going to be -26. So for question 2, we're asked to find first of the following absolute value functions. We're asked to sketch and label the x-intercept of the function and express the function in piecewise notation. So we'll first begin by graphing. So as you'll remember, the absolute value is the amount of units from 0, right? So all we're doing is if our value is negative, we're making it positive. So wherever this graph is negative, we're just essentially flipping it and reflecting it along the y-axis. So let's say we had a line that looked like this normally. If it were the absolute value of this graph, it would look something like this. So now, actually graphing. So to begin with, we have to look at this. +4 is our y-intercept, so we're going to plot this point as our y-intercept. Our slope is going to be -5/3, so rise over run. If you remember from math 10, we did rise over run. So what we can do here is we're going to go up 1, 2, 3, 4, 5 units, and we're going to go left 1, 2, 3, since we have to make that a negative, right? And now we're going to be going down 1, 2, 3, 4, 5, 1, 2, 3, right. And you can do this so on and so forth until you get a nice little looking line here. So something that looks like this. I mean, it looks like a line of best fit right now. And that's not what we're trying to go for. So just pretend it's a really nice line and not this line of best fit. Anyways, that's besides the point. We've actually graphed the original function. All we're doing now is any point past our x-intercept, you'll notice, is going to be negative. So all we're doing is any point past that, where x is greater than, in this case, our x-intercept, we're reflecting it along the y-axis. So let's reflect this here, and it'll turn into something that looks like this. And that'll be your absolute value graph. I mean, it's not perfect, but again, it's going to look a little weird. So now you're asked to find the piecewise notation, or express this function in piecewise notation. So how do we actually express something in piecewise notation? So to begin with, we have to write brackets that look like this. F of x is equal to, and then we can make these nice little squiggly brackets. And now what we can do is write our first portion of our piecewise notation. So all piecewise notation is effectively you have x where it's positive and x is greater than 0, and you have negative x where x is less than 0. And I'll show you what this actually is going to mean and start to look like. So we have the function negative 5 over 3x plus 4. And we're going to add a comma here, because we're going to add our now x-intercept, right? So we have to actually look where our x-intercept, since we're taking the positive version of this expression. So the positive version effectively is the line that we drew over here. This is one version of our equation. So where is x have to be, or what values of x are we changing and flipping in this absolute value equation? So you'll notice we're flipping any value that is greater than, or in this case, or equal to, since it's the positive x version, than our x-intercept. So let's find our x-intercept. How do we do that? We have to set f of x equal to 0. So 0 equals negative 5 over 3x plus 4. So now all we have to do is subtract 4 from both sides, and get 5 over 3x. Multiply both sides by 3. Get negative 12 equals negative 5x. And then you're going to get positive 12 over 5, which simplifies to and 12 over 5 is going to be equal to 2.4. So you can leave it in this, since it's a nice fraction. So now we've actually found the intercept as 2.4. What we can do is we have to figure out what we have to do with this. So the original equation, or our original equation, which we don't change, because remember there's two cases to our piecewise notation. So we have x, or just our original equation here. And all we're doing is we're expressing where our original equation was already positive. So you'll notice, you'll see that our line slopes down and goes negative. It goes negative where x is greater than 2.4. And it was already positive where x is less than 2.4. And this is absolute value. We're looking for where it was already positive, right? So we're going to have x is less than or equal to 2.4. Because remember, this is our original equation, so we're using that less than or equal to 2.4. And the other one, or the other option here, is going to get slammed in with the negative version. So we'll have this negative version of 5.3x plus 4. And you can leave it like this, or you can distribute this negative one, which I'll do here. So to distribute this, you just multiply. And then we have the negative version. And then we have the negative version of our graph here. So we're going to have negative 5 over 3x, negative 5 over 3x plus 4. And when you distribute that negative 1 onto everything, it becomes positive 5 over 3x minus 4. And this graph is going to be going the other way. So all that is where x is greater than 2.4. And that is how you do the first part of our piecewise notation. So now, this one's a bit tricky because the last one was actually a linear, but this one is going to be a quadratic, and it's going to be expressed in terms of g of x. So the way we do this is we're going to write out g of x is equal to, and then we're going to put these nice squiggly brackets, of course, and we have to find our x-intercepts here. So if you remember, all we have to do to find our x-intercepts is we're setting y, or in this case, g of x, equal to 0. So 0 equals negative x minus 4 squared plus 9. Subtract 9 from both sides, and you get negative x minus 4 squared. Divide by negative 1 to cancel out this negative sign. You get 9 is equal to x minus 4 squared. And then you're going to take the square root, so you're going to get plus or minus 3 is equal to x minus 4. Add 4 to both sides, and you'll get plus or minus 3 is equal to x. So your two solutions of x is going to be 1 and 7. So now that you found your two intercepts, you can begin to graph your original equation. So we found our two intercepts as our original equation of being 1 and positive 7. So positive 1 and positive 7. And remember that our a value here is negative, so we're going to have a maximum. It's going to look something like this. Not exactly, I'm not going to get too practical with it, but it's going to look something like this. And then any point beyond these x-intercepts are going to be negative. So if we were to write a piecewise function for this, all we're doing is we're taking these bottom points and we're reflecting it along the y-axis again to make it positive. So we have to state where our original graph, this original equation here, so we'll write it out, negative x minus 4 squared plus 9. And then we have to write our domain for where it was already positive. So how do we do this? Where was our graph originally positive? Between these 2 points, right? Because nothing changed. Where it did change, though, is past these x-intercepts. So where it was already positive was between 1 and 7. And since this is our original graph, if we go back to over here, we're using greater than or equal to. So let's use greater than or equal to. So x is greater than or equal to, we'll have this domain here, but with or equal to signs at the end of it. So we'll have 1 is less than or equal to x, which is less than or equal to 7. And it's the or equals to sign because it's our original equation. Again, now, what we're doing is our portion where it's negative, right? So we have to take the negative version of our equation. So if we were to multiply this by a negative, these negative signs would cancel out front. So I'll show you. X minus 4 squared plus 9. These negative signs would cancel out. So all you're left with is this equation here, which is the negative version. Because remember, when we're dealing with absolute values, there's two cases, the positive and the negative. So this is where it's negative. And you'll notice that this parabola has a positive a value, has invisible 1, and it's just going to be the exact same parabola, but just flipped, where we need to actually take a look at it differently, because these two arms were initially already positive, right? And we're flipping this bottom curve, whereas on the red line, it was the opposite. So where x is less than 1 and x is greater than 7, in this case, is where our original or our negative equation had already had positive values. So x is less than 1, and you write and x is greater than 7. And that is how you write a piecewise for a absolute value function. So we're asked to solve each of the following absolute value equations algebraically and find the extraneous roots. So when we're dealing with absolute value equations, they have two solutions. And what does that mean? To have two solutions, it's weird, right? So we have our first case, because I mentioned this earlier. We have case 1, where we have the positive version of our equation. It doesn't have to be case 1 necessarily, but case 1 in this example will be positive, and in case 2 will be negative. So let's do this. So in order to solve for this, the first step I would do is I would isolate this absolute value symbol. So let's subtract 5 from both sides, and you're going to get the absolute value of 7x minus 3 is equal to x plus 1. Now, once you've done that, we can actually do this. I mean, it's not something you have to do, but it's the way we can eliminate a step and make this a little bit easier. So all we're doing is we're taking the positive case. So if this were positive, we're just multiplying a positive 1 onto here, and you're getting 7x minus 3 is equal to x plus 1. Now it's a matter of actually solving for x. So the way we do this is we can subtract 1 from both sides, and you get 7x minus 4 is equal to x, and then you get negative 4, and then equals negative 6x, because you subtract 7 here. And now you get negative 6x is equal to negative 4. Divide both sides by negative 6, and you're going to get negative 4 over negative 6 is equal to x, which simplifies down to 2 over 3. So 2 over 3 is our first solution. Now let's do case 2. So now for case 2, what we have to do is we have to set it negative this time. So last time we multiplied whatever is inside our absolute value sign by positive 1. Now we're going to multiply it in by negative 1. So we have negative 1 times 7x minus 3 is equal to x plus 1. Now we distribute this onto here, and you're going to be left with negative 7x plus 3 is equal to x plus 1. Now all you have to do is you have to subtract both sides and isolate for x. You're going to get negative 8x is equal to negative 2. Divide both sides by negative 8, and you're going to get negative 2 over negative 8 as your final answer, which simplifies down into 1 over 4. So now that we've found both solutions by checking out both cases of our absolute value sign, what we can do is we can plug in our values of x, which is going to be 2 over 3 and 1 over 4, to see if these are extraneous solutions, meaning if we reject it or not. So let's test out our first one. So the absolute value of 7 times 2 over 3 minus 3 plus 5 should be equal to 2 over 3 plus 6. So if you put this side into your calculator, you're going to get approximately 6.6 repeated, and this should be equal to our right side. So if we plug in the right side of our equation, this gives us 6.6 approximately, which are equal. So left side is equal to the right side, meaning this solution is not extraneous. So this is going to be correct. Now we have to test out our solution of 1 over 4. So the way we actually do this is we're going to have to use the same method. So we have to plug in 1 over 4. So 7 times 1 over 4 minus 3, and we're taking the absolute value of that, plus 5 should be equal to 1 over 4 plus 6. So if you plug all of this into your calculator, you're going to get 6.25, which should be equal to 6.25. And left side equals right side, so this root is not extraneous either. So there are no extraneous roots here. So now moving on to this one. This one's a quadratic one, so it might have around 4 solutions since we have 2 cases and each quadratic has 2 solutions each. So that will give us a net of 4 solutions, hopefully. So let's see. Let's do case 1 and let's set this as positive. So our positive case here becomes x squared minus 8 is equal to 8 minus x. Since we multiplied a negative 1, a negative or a positive 1 onto our whatever's in our absolute value sign. So now what we can do is we can subtract 8 from the side and add x, and you're going to get 7x squared minus 7x. Since we've added that x, minus 8 is equal to 0. Now we can solve this. We can solve for x, whether you want to use quadratic formula, whatever. All you have to do is just find the 2 factors of this equation. So we have to find 2 things that add to negative 7 but multiply to give us negative 8. So you'll notice your 2 numbers here are going to be 1 and negative 8 and 1 plus negative 8. We're going to factor by inspection, and we're going to get x plus 1, x minus 8, which turns into x equals negative 1, comma, positive 8. And those are the solutions for the first case, which we set as positive. And we're going to have to test each individual solution, so make sure you're making sure you're keeping track of this and keeping it real neat. So we have case 2, which I'll set to be negative. So we're just multiplying whatever is inside our absolute value sign strictly and only in our absolute value sign. So we're going to have negative times x squared minus 8x turns into negative x squared plus 8x, which is equal to 8 minus x. You're going to add x to both sides, and you're going to get negative x squared plus 9x minus 8, which is equal to 0. Now what we can do is we can actually divide both sides by negative 1, or everything by negative 1, to make this factorable. So this turns into x squared minus 9x plus 8, which we can now begin to factor. So the way we can do this is this will turn into, we have to find 2 numbers that multiply to 8 and add to give us negative 9. So we have negative 8 times negative 1 and negative 8 plus negative 1. So since this is factored by inspection, we can write this as negative x minus 8 and x minus 1. So now we can find our roots by setting each individual factor equal to 0, which will give us x equals 8, comma 1. So these are the 2 solutions for this negative case. You'll notice that we have overall 4 solutions, or 3 solutions total, because we have both answers as 8. So it's typical that you will have this amount of solutions because this is how the quadratic absolute value functions are set up. So what you have to do is, if you're getting a value that is like an exact value, like let's say you use quadratic formula and your answer was 24 root 3 over 9 or something like that, right? Or plus 24 plus or minus root 3 over 9. What you would have to do is you have to actually store this as x in your calculator and then plug it in for x when you're double checking. But since we have nice numbers here, we don't have to do all of that. If you were to double check all of these solutions, they would be correct. I'm not going to do that because I want to save time on this video. But none of these are extraneous. However, if your solution did not match up, left side did not equal right side, that solution is labeled as extraneous and you can get rid of it. So now, one thing I actually want to show you guys is how to actually use some of this technology and apply how to use technology to solve an absolute value equation. So let's go into our calculator here. So I pulled out my calculator here. I'm gonna make it bigger. And what we're going to do is we're going to type in this part of our equation as the left side. So what I mean by that, we'll type this out as y1. So the left side is going to be y1. So we have 8 minus x as y1. We're going to go to the bottom and we're going to type out the right side of our equation as y2. So we have the absolute value of x squared minus 8x. And if you're wondering how to go to absolute values, all you have to do is you just have to press math, scroll one over, and then hit absolute values. That's how you double check. Now you're going to hit graph, and you're going to test all of your solutions. All your solutions are going to be the intersecting points. So the intersecting points between all three of these graphs are going to be your answer. So you'll notice that we have our intersections as, let's see. So our first intersection here is -1, which is one of our answers that we got earlier. Our second intersection here is +1, which is what we got earlier as well. And our third answer here is going to be +8, which we got as well. And these are all correct solutions because they all match up and intersect in the graph. So that's how you know if you're right. And this is a way of double checking your solution in terms of absolute value equations within your calculator. So now moving on to reciprocal functions. A reciprocal function is typically going to just look like 1 over x or 1 over f of x. So all it is in essence is we're just looking for a couple things. One thing that's really crucial to understanding absolute value and reciprocal or just reciprocal function graphs is the invariant points. So I'll write invariant points are the points common between both the absolute value graph or are the points common between the reciprocal function graph and the normal graph. So they share common points. These points don't change regardless if you take the reciprocal of it. And those points are where y is equal to 1 and y is equal to -1. And make sure you remember this. Additionally, when you have a quadratic, all that's going to happen is you're going to have your vertex being changed to p, 1 over q. So that will be your new vertex. You're going to have p, which turns into 1 over q. So your x value is going to stay the same. All that's going to change is you're going to put 1 over your q value of your vertex. So let's try this. So for each graph, sketch the reciprocal function. So here we actually have to find our equation of our line first. So how do we do this? So the way you actually sketch the reciprocal of this function is you have to find its horizontal and vertical asymptotes. So you'll notice that our horizontal asymptote, in terms of horizontally speaking, is going to be y is equal to 0. So when we're dealing with reciprocal functions within Math 20, your horizontal asymptote is always going to be 0. So horizontal asymptote is y cannot equal 0, but since we're drawing this line here, y is equal to 0. Now, our horizontal, or our vertical asymptote is the one that's going vertical, so where our x-intercept is. So we're going to draw a dashed line here, where our vertical asymptote is the x-axis, or the x-intercept, so where it crosses the x-line creates our horizontal asymptote. So this is approximately 1.5. I know it's not a great looking graph, but our horizontal or vertical asymptote looks to be about 1.5. Now, you'll notice that the only points that stay the same here are going to be your point where you have 1 and -1. So we have to meet these points on our graph and actually graph it out. So since we have these barriers here, I'm going to draw this out better. So you have a blue line, and then you have the red line barrier. Our new equation, or our new sketch of our 1 over f of x is going to look something like this. Because it's going to try to go straight, but it's going to get curved by the horizontal and vertical asymptote. Same thing goes for here. And it'll look something like this. Now, in terms of this one, our vertex here looks to be about 1, 9. So 1, 9 is our PQ. We said that when we take the reciprocal of our function, all we're doing is we're turning our y value into 1 over that q value. So we have 1 over 9 as our new vertex. So 1 over 9 is a really small number, so it's going to be approximately right here. Now, let's look for our invariant points. So y is -1. So dunk 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 over here, and over here is where y is -1. Now we need to look where x is +1. So right here and right here. And we need to draw horizontal and vertical. We need to draw the horizontal asymptote. So this axis is going to be our horizontal asymptote, where pretend it's dashed, but you can't really see if it's dashed. So this is where y equals 0. And we have the horizontal asymptotes where we have our vertical asymptotes where we have our x-intercept. Remember this, where it crosses the line is the x-intercept. So you're going to create these vertical asymptotes, which is approximately x equals 4 and x equals -3. This is approximate, it doesn't have to be perfect. And now all you're doing is you're drawing your graph. So this point is going to look like this. This point is going to look like this. Or it's going to come down a bit more. It's going to try to touch the walls of everything. It's going to look something like this. And then on this side, it's going to create this U shape here. And that is how you sketch the reciprocal function version of this graph. So now we're asked to sketch the reciprocal function from scratch. So how do we do this now? Now, how do we do this? Okay. One way we can do this is we have to draw out our original equation. So we had x squared plus 2x minus 3. So we have to draw this out like we would normally. So to draw this out, you have to find the roots, right? You have to find the x-intercepts. So let's find our x-intercepts here. Let's factor this. So this factors down into x plus 3 and x minus 1. And you're going to get your roots as -3 and 1. So you have this point here and -3. Cool. We found our two roots. Now we can see if it opens down or up by looking at the a value. So the a value is going to be positive. So if it's positive, that means it opens down. So we're going to get something that looks like this. So our vertex here is going to be -1, 4 if you were to graph this in your graph. And that is our original version of this equation. So it'll look something like this. And I like to graph the original because it gives you like a reference to see what you're kind of doing, as it's easier to graph from a graph than graph from scratch, especially with these reciprocal function ones. So it'll look something like this. It's not perfect, but it'll do for now. So now what I'm going to do is we're going to draw our vertical asymptotes. Because remember, vertical asymptotes in this is going to be y is equal to 0. And then our horizontal ones are going to be our x-intercepts. So where are these points? We're going to draw these dashed lines. Because remember, the dashed lines mean we cannot be equaling. And these dashed lines happen where x is equal to -3 and x is equal to 1. Now, what we can do is we're looking at our invariant points and we're drawing them. So -1, our invariant point is going to be about right here. or sorry, our invariant point is going to be just before this. Our invariant point here is going to be just before this. It's not a perfect drawing, but it captures the essence. And remember that our vertex was 1, negative 4. Since it's a reciprocal, we're taking the 1 over the q value. So our q value is negative 4, so we have 1 over negative 4, which is about negative 0.25. So we're going to have our vertex be about negative 1, 0.25. So about right there is going to be our new vertex. So now we can draw out this reciprocal vertex here, and it's going to look something like this. Now, in terms of 1, our invariant points at 1, we're going to look here, and we're going to have these 2 points, or these 2 arms, which reach out. This is going to turn into this, and you're going to get something that looks like this. And you've successfully graphed you've successfully now graphed your equation that models 1 over x squared plus 2x minus 3. Now, if they're asking you to be specific, the way you can find the invariant points is you have to set y equal to 1 and y equal to negative 1. And all you would do is you would do that and then subtract it from both sides and then factor that new quadratic that you're going to get. So for example, we have 1 where y is equal to x squared plus 2x minus 3. You subtract 1, x squared plus 2x minus 4. And then you have to find the x-intercept here. And then you're going to get x equal to 1.2, comma, negative 3.2, which are your invariant points, same throughout each graph. So approximately 1.2, where x is 1.2, and 1. So 1.2, so around right here, comma 1, which is what we got approximately. But again, if you want to be exact, do this for sure. And then you would do the same thing for the negative 1, which turns into x squared plus 2x minus 3. You add 1 to both sides and you get 2x plus 2x minus 2. This gives you roots of 0.7 and negative 2.7, where y is 1. And then again, where that would be representative of these points. And then you can find the vertex by putting 1 over that q value. So again, it's just if you want to be approximate, cool. But I don't really have the time for that right now because I want to get through everything that I can as fast as possible. So definitely do this if it's a written response. Don't just like eyeball it like I did. Now, determining the equation from a graph. So how do we do this? So remember, our invariant points are crucial because they're points that are similar throughout. We know this is a linear since we only have one horizontal or one vertical asymptote. When we have one vertical asymptote, that means we have a linear function. If it is 2, as you'll notice, since we have 2 horizontal or 2 vertical asymptotes in this line, it'll be a quadratic. So we're dealing with a linear equation. So we have y equals mx plus b. Now, do we remember how to find m? Of course we do. M is equal to y2 minus y1 over x2 minus x1. So this formula gives you slope. And what do you notice? We have 2 points that can help us find the slope. So we can actually use this. So m is equal to whatever you want to set. I'm going to set this equal to x1, y1, x2, y2. And you're going to get 1 minus, so our y2 is 1 minus our y1, which is negative 1, over x2, which is going to be 1 minus 3. So this turns into 2 over negative 2, which simplifies further down into negative 1. So our slope here is negative 1. So negative 1 is equal to m. So now using the slope, what we can do is we can actually find our vertical or our y-intercept. So you remember from math 10, we go up 1, left 1, up 1, left 1, since it's a negative slope. Up 1, left 1, and then now you've reached your y-intercept where b is equal to positive 2. So now you have your equation. You have y equals negative x plus 2. And that is your final answer. Now, if we were asking you for the reciprocal, all you'd have to do is you just have to graph this equation here, negative x plus 1 over x plus 2 equals f of x. You put this into your calculator and see if it matches up. And if it does, has similar points, then you have done this correctly. But the answer here is going to be y is equal to negative x plus 2. Now you may be wondering what it might look like if we're asked to do domain and range, right? So if your line is linear, you have one vertical asymptote. All your domain is x such that x cannot equal whatever your horizontal asymptote is. In this case, it was 2, so x cannot equal 2, and x is an element of the reals. Make sure you know how to do domain and range with these functions. Now for something more complex like this, our domain and range gets a little blurred. You're not unsure what to do. So if we were to do domain, we have our domain where we have, our domain where x such that x cannot equal our horizontal asymptote. So all our domain is our horizontal asymptotes. So we're saying x cannot equal 4 in this case and negative 1. Now in terms of range, it gets a little tricky here because you have to look and analyze, right? So the way we do domain and range, or the way we do range in particular, is we're going to have to evaluate this by seeing what y cannot equal. So y such that y obviously can equal 0. This point is just going to be y cannot equal 0, and y is an element of the reals. Now same thing goes for this linear line here. We have y such that y cannot equal 0. Now for our absolute value graphs, if we go back, all y absolute value graphs is for domain, we have x such that x can be an element of the real. So any time, any place, x is a possible number. Now in terms of domain, we can't have any negative numbers. So the way we actually express that is y has to be greater than or equal to 0. And y is an element of the reals. And that goes for basically every absolute value graph. It's going to have these exact two domains. So now we have the word problem here. A computer controls the amount of fish that is packaged in a specific size can. The program sets the ideal mass to 170 grams, but allows a difference of 6 grams. So we can model this by using the absolute value equation. So we're going to create an absolute value equation. We can have 170 grams, but we need to subtract it by something, by a number, which we're going to represent as x, which can only allow us to have a difference of 6. So it's not going to be an equal to question, it's going to be an inequality. The reason being is we can have any number in a range that'll give us a difference of less than 6. Because we're allowed to have a difference of 6, but also anything that's less than 6. So we can have 6, which is why we put the I or equal to sign, and we have less than because we don't want our difference to be greater than 6, otherwise it would be sent out. So now you may be wondering, like, what's going on here? We did absolute value equations. This is different. This is going to be the same property and same idea, which we're going to be using here. So we have case 1, where we're doing the same thing. We have the positive version, so we just keep it the same. And we're just solving the inequality this time. And thank God it's not a quadratic one. But if it were, you guys should remember and recall how to do this from our unit 3. So we have negative x. You're going to subtract 170 from both sides. And you're going to get x is less than negative 164. You're going to divide both sides by -1. But remember, when we divide by a negative sign, our sign flips. So we get x is greater than 164 as our first answer. And then we have case 2, where we have a negative. So we just multiply 170 by -1 and then negative x by -1. So we get -170 plus x has to be less than or equal to 6. We add 170 both sides and get x is less than 176. So if we're looking for the minimum mass and the maximum, the highest value that it could be is 176. The lowest is 164, which allows a difference of 6 at the most. So the way we can express this is 164 is less than or equal to x, which is less than or equal to 176. So any value of x which is within this range will give you something that is either give you a difference that's either equal to 6 or less than 6, which is good, which is what we want. So that is how you solve this question.